We also have this question of kinetics, which is asking a different question. It's concerned with, regardless of which is favored at the end of the day, reactants or products, how fast will we actually be able to get to the reactants or the products? And so the way that we answer this is not with the difference in the energy between the reactants and the products, but just how much energy we have to put in to make the journey from the reactants to the products. So an analogy is if you are riding around Lynchburg and you have a bike and you're trying to get to Kroger, you could take a variety of different paths. And Lynchburg is very hilly, and you would definitely want to choose the path that has the smallest hill. And so if you rode, let's say, a bicycle over this hill, you have to put in a certain amount of energy to get over the hill and get to your destination. So the energy that you would have to put in for this example would be this much energy. So you could measure that energy, and this actually has a certain name in terms of chemical reaction, and this is called an energy of activation, and the symbolic name of this is delta G with a little double dagger in superscript. So this is one hill that you could choose from where you have to put in a lot of energy to go over this hill. Another alternative is you could potentially go on Google Maps and try to figure out another path to get to your destination over here, and you might select ride your bike over a hill, but in this case this hill has a much smaller energy associated with it. So really, if you had to describe how fast it takes you in this first scenario versus how fast it takes you in the second scenario, you could say then that the second scenario is actually a faster reaction than the left-hand scenario. And then simply because you have to put in less energy, and so it's going to be much more likely to happen. So the last little thing we're going to talk about is whenever you have more complex reactions, where you have multiple steps to get from the starting material to the product. A lot of the times reactions aren't as simple as just saying beginning and end with nothing in between. A lot of the times you have a lot of these hills and valleys. So what you can do is, before we've already talked about local maxima, and we said that these guys were called transition states. I'm just going to abbreviate it as a TS. So we actually have two transition states for this particular reaction that's just completely generic. We have one transition state here, and we have one transition state here as well. So we also have this valley right here, or this local minimum. And if you have a starting material and a final product, and in between you see these local minima, these have a specific name as well. These are called intermediates. So intermediates are a species where you've actually already formed all of the bonds that you're going to form, and you've already broken all the bonds that you're going to break, and they're an actual molecule that you could actually isolate and take a look at, but they don't necessarily hang out for very long. So they're still very high energy, much more so than the starting material of the product. So they're going to try to go somewhere else that's a little bit lower energy. So anyway, the difference between the transition state and the intermediates have all of their bonds made and broken. Transition states are these weird intermediate times, or in-between times, where you have bonds that are partially made and partially broken. So if you actually wanted to go from the starting material to the product, you could try to talk a little bit about kinetics and ask the question, what's going to be the bottleneck? What's the biggest hill that we have to go through? And the answer to that is, you try to find the transition state that has the highest energy, and that's going to be this transition state on the left right here. So it turns out that if you wanted to talk about this bottleneck, it has a specific name, and it's called a rate determining step. And this rate determining step is going to be the transition state that has the highest energy.